So this is a resource for you to refer back to regarding heating curves. Okay, so we talked about heating curves a little bit in lecture, and it is just the relationship of the heat that's added for any system and the temperature that's associated with that heat added. And remember, heat here is a form of energy, right? And temperature is a way that we measure the change in heat, okay? So as you are increasing along the x-axis here, more and more heat is being added, okay? And as you see, as more heat is added to the system, the temperature of the overall system increases. So every compound has its own specific heating curve, and it will absolutely depend on the melting point and the boiling point of each of those compounds. The melting point is the line that we see right here, okay? This is the melting point where there is an equilibrium reached between the solid and the liquid phases. This incline right here is the solid, and this is when the compound is totally a liquid. There is no solid or gas in there, okay? And this melting point right here is where there is an equilibrium between the two, okay? This line right here indicates that you're still adding heat to this overall system, but because the compound is transitioning from a solid to a liquid, the temperature does not change. And this is the corresponding melting point. Now similarly, the boiling point is indicated by this part of the graph right here, okay? This is your boiling point. So similarly to the melting point, this is when the liquid and the vapor stages are also in equilibrium, right? Remember, so we talked about when the heat is added to the system, the temperature will not increase until all of the liquid has been transferred to the vapor stage, okay? And at this temperature is where you have your boiling point. So when we are doing problems regarding heating curves, we are trying to figure out how much heat is added in conjunction with a phase change. Okay, so we have a couple of different formulas that help us do this, right? We have the regular, what you have already learned about, the Q equals Sm delta T here, right? Where the Q is the heat that's been added to your system, okay? The S is the specific heat of any given substance. The M is the mass of that substance, whatever it may be, and the delta T is the amount of the temperature change that we are trying to figure out how much heat can make this delta T happen, okay? So if you can use this whole equation here on any part of the graph where there is a delta T. See how, say this is at T equals 0 here, and say this is T equals 10, so you have a delta T of 0 to 10 here, or 10 degrees would be your delta T. So while we are trying to figure out the total amount of heat added, we also have two different equations that can tell us the amount of heat that is responsible for changing a substance from a solid to a liquid or a liquid to a gas, okay? So with this first equation, we're going to be talking about this heat change right here. And what this is called is the delta H of fusion. Okay, so you have the delta H of fusion. This is just the amount of heat that's required to convert 1 mole of substance from a solid to a liquid. Similarly, we also need a value that will help us calculate the amount of heat that's added when you are going from a liquid to a gas. And that is called the delta H of vaporization. And this is technically defined as the amount of heat that's required in order to have 1 mole of liquid be transitioned into 1 mole of gas. So now let's apply all of these ideas to a problem. So up here at the top, I have a problem that says find the heat in kilojoules absorbed when 24.3 grams of water is heated from 85 degrees Celsius to 117 degrees Celsius. Okay, so if we are taking this heating curve that I have had on the video as the heating curve of water, we can assume, right, that this part right here is your 0 degrees C, okay, and this is where your 100 degrees C will be. And we just know that because of 0 degrees C being the melting point of water and 100 degrees C being the boiling point. So with this problem, we want to look at what the change will be when we start at about 85 degrees C here and go to about 117 degrees C on our heating curve. And as you can see here, we go through a phase change such that there has to be a certain amount of heat incorporated in order to compensate for the water going from the liquid phase on this side of the curve to the gas phase on this side. And right here is where we have our delta H of vaporization. So in solving this problem, we'll be using the Q equals SM delta T to figure out how much heat is needed to raise the temperature of the water this many degrees, and how much heat is needed to raise the temperature of the water when there's a delta T of 100 to 117. Okay, and we're also going to need the amount of heat that it takes to convert this many moles in 24.3 grams of water from the liquid phase into the gas phase. So now let's try it. So the first thing we need to do is take our 24.3 grams of water and convert it to moles. So we have 24.3 grams times mole over 18.02 grams of water, and this ends up giving us about 1.35 moles of water. So I will go ahead and move this calculation off to the side for us to use later, because first I want to figure out what my Q will be when I know that my first delta T for this portion right here will be 100 minus 85. Okay, because we are figuring out how much heat it takes to increase the liquid water from 85 degrees Celsius to 100 degrees Celsius before we get to the boiling point. So the specific heat of liquid water is 4.18 joules per gram Kelvin, right? And the mass is 24.3 grams, and our delta T is 15 degrees Celsius, okay? So if you multiply these all together, we end up getting 1,524 joules. Or another way to say that is 1.524 kilojoules. So just for organization's sake, I put the amount of heat that we just calculated over in this nice little table to make sure that we are keeping up with all of the temperature changes that we need. So next we're going to look at the amount of heat that's needed to be added while we are going from the liquid phase of the water to the gas phase, right? And this is what we talked about with the boiling point. So here we'll need the delta H of vaporization, which is 40.7 kilojoules per mole. Now remember that an enthalpy change is always expressed in kilojoules per mole, okay? But what we just want is kilojoules. However, lucky for us, we already calculated the moles of water that are being heated. So we just multiply our delta H of vaporization by 1.35 moles, and that gets us to 54.9 kilojoules. So I'm just going to add this data up to our little table. So the last part of this problem is just figuring out how much heat needs to be added to the 24.3 grams of water in order to get at this last 17 degrees up in the vapor stage. Okay, so we utilize the same equation that we did before with the Q equals SM delta T, okay, where our delta T is equal to 17. All right, so if we write this out, now a little bit of a difference here, the specific heat of water vapor is different than that of liquid water. Okay, so the specific heat of water vapor is 1.996 joules per gram Kelvin. Okay, and we're still using the same mass. Okay, so we have 24.3 grams. I'm getting a little crowded here. Times the 17 Kelvin for our delta T. And that overall heat comes out to, once you calculate everything out, it's 825 joules, which can be interpreted, of course, as 0.825 kilojoules. So now let's just go ahead and add that to our table. So once we have the three different heats all in kilojoules, we can add those up to get to an overall heat of 57.25 kilojoules of heat needed to heat 24.3 grams of water from 85 degrees C to 117 degrees C, taking into account the phase change of going from a liquid to a gas.